So for a hyperbola, it's the set of all points in the plane, the difference of whose distances from two fixed points. We know now that those points are called the foci, is a constant. So just one more time, if I took this point D and moved it around this side of the hyperbola, the individual distances from each focus is different, but if you subtract them, that running total here is staying the same. No matter where that point D there gets dragged. Same thing here. If I take any point along that side of the hyperbola, the difference is 2.85. Here the difference is 2.85. Okay? So, let's take a look at the equations. They're very, very similar to that of an ellipse. There's one big difference. Split your paper again. We'll take a look at the one that's horizontal and compare that to the equation of a hyperbola that's vertical. So the equation of a horizontal hyperbola is x squared over a squared minus y squared over b squared equals 1. Now this is where it gets a little bit different. Well, what's the big difference here that you notice right off the bat between this and an ellipse? Subtraction, okay? And the other big difference, and some students really have a hard time remembering this, is it doesn't matter which is bigger, A or B, they just both have to be bigger than 0. A doesn't have to be bigger than B. That's only true of an ellipse. B could be larger than A. It doesn't matter. Okay? The reason it matters with an ellipse, and let's just go back here real quick to help you remember from last time. So you don't really need to add this onto your notes because you already have it. This equation here, this is the equation of an ellipse. This is what we learned last time. Would that be a vertical or a horizontal ellipse? The way that I taught is you look for the larger number. It's underneath the y variable, correct? That would be a vertical ellipse. It would be some kind of ellipse that's elongated that way. Okay? That makes this a squared. In ellipses, the larger value is always a squared, but that is not true with hyperbolas. Okay? If it's a horizontal hyperbola, whatever's underneath x squared, that's a squared always, regardless if it's bigger or smaller. Whatever's underneath y squared, that's going to be b squared, regardless. Okay? So that's just something you're going to have to try to remember and keep track of. The vertices are plus or minus a comma 0. The location of the two foci are plus or minus c comma 0, where c squared is equal to a squared plus b squared. Now, do you see another big difference between hyperbolas and ellipses? This is a squared plus b squared to help you find c squared. With the ellipses, it was a squared minus b squared. Okay? So let's just do a quick sketch of a horizontal hyperbola. The vertices are plus or minus a comma 0. So let's go over here, and we'll call that positive a, We'll come over here and call that negative a. Okay. The foci are located inside each curve of, so we'll call that C, and we'll call that negative C. Those are the two foci. It's just a rough sketch. We're going to learn how to sketch these more accurately here in a second, but this is what a horizontal hyperbola would look like. Okay? Here's the equation of a hyperbola that would be considered vertical. Vertical would be coming up and coming down on either end. Okay? Vertical is y squared over a squared minus x squared over b squared equals 1. You guys have got to come up with a way to try to keep these straight. How can you recognize a vertical hyperbola compared to a horizontal hyperbola? The way I try to remember it is which one is the positive term. Okay? This vertical one, which one's the positive term? The y squared term is positive. This is a vertical hyperbola. Over here, the x squared over a squared is the positive term.
Will you ever get to negatives?
I suppose you could, but not in this section, no. So this is a vertical hyperbola. Okay, the vertices are 0, comma, plus or minus a. That would place them on the y-axis. The foci are 0, comma, plus or minus c. That also places them on the y-axis. It's still the same formula. C squared equals a squared plus b squared to find the foci. Hey man, are you just getting to school?
Yeah.
Oh man.
Yeah.
Oh yeah, we're having a blast, aren't we guys? Aren't we?
Yeah.
Okay, so the two vertices are at a, negative a on the y-axis. The hyperbola would look something like this, where the two foci are located on the inside. We have C and negative C. So that's a vertical hyperbola. Unfortunately, nowadays there aren't as many practical applications for hyperbolas. I mean, the reflective properties in microscopes and I don't know. In microscopes and telescopes, they used to use it a lot in maritime navigation. Do you know what I'm talking about?
Not at all.
It's kind of like sonar. It's been replaced with GPS. GPS has been around for a while, but before GPS, there was a location system called LORAN, L-O-R-A-N, that used hyperbolas to locate ships at sea using two fixed points. It was kind of cool, but it's kind of obsolete now.
So what you're saying is you're teaching us primitive math.
No, they still use this in biology and things like that to help make microscopes and telescopes. But it's still conic sections, so we can't really study conic sections without studying hyperbolas. Anyway, let's graph these. The way that we graph these is also going to be much, much different than we graphed an ellipse. So we're going to graph 9x squared minus 16y squared equals 144. First trouble is this is not the form of the equation we need. It's the equation of a hyperbola. It doesn't look like either one of these. First thing that should pop out to you is it doesn't equal 1. We looked at something like this yesterday, or last time. How can we make it equal 1? Divide by 144. So now the right side equals 1. This term, though, 9x squared over 144. What happens? close. 16. 9 over 144 is the same as 1 over 16. That's how the fraction reduces. So this term here becomes x squared over 16. And what about 16 over 144? That's 1/9. 16 over 144 is 1/9. So this turns into y squared over 9. Now it's in the form that we need. Yeah, and that's the next question I was going to ask. Vertical or horizontal? And the term that's positive is the x squared term. That's the positive term, so this is going to be horizontal. Okay. And it also matters which one is a. And it's not just because this is the biggest number. It's because it's underneath the positive term. Okay, so this is a squared, which makes this b squared. B squared equals 9. If a squared is 16, then a is plus or minus 4. And b is plus or minus 3. Now, this one you have to pay attention to really good because the process is slightly more complicated. Graphing an ellipse was super easy. You put the endpoints of the vertices, you put the endpoints of B, and you graph the ellipse. Not quite as quick here. You still have to graph the vertices. Positive 4, negative 4. Those are your two vertices. Okay. Now I mentioned this, but you may not have heard it, so I'm gonna show you this picture one more time. I'll get back to this. Do you remember how I said there's a slanted asymptote running right through here? Okay, and there's another slanted asymptote running right through here that will give you the correct behavior of the end behavior of these. Do you remember I said that? Well, we need to know exactly what the slope of those two slanted asymptotes are. And here's one way you can find it. This is not the only way you can find it. Here's one way. You place B on the y-axis. And then you draw this rectangle. This is what's referred to as the central box. This box doesn't actually exist as part of the graph. It's simply an aid to help you get a better shape of the graph. This is called the central box. Okay. Now, locate the corners. Okay, and then draw lines going through the corner and the origin. This is one of the slanted asymptotes. The other one is going through the other corner, through the origin.
Why do they go through the origin?
Because this is centered around the origin. Again, these lines don't actually appear on the graph. They're simply here to help us aid.
Pardon the interruption. We need Jesse left in the front office.
Okay. So now, what kind of ellipse, what kind of hyperbola was this? Remind me. Vertical or horizontal? Horizontal. That means it's going to fit here in the right part and over in the left part, correct? So now we have the vertex on each side. We have a vertex here and we have a vertex here. So all you need to do is have this piece kind of follow the behavior of that asymptote. It needs to curve through that vertex and then come over here and follow the behavior of that asymptote over there. There's one piece of the hyperbola. The other one's going to do the exact same thing over here. It's going to kind of skim along that asymptote, curve through the vertex, and then follow that asymptote out to infinity. That's actually what the graph is, those two pieces of the hyperbola. These others, you wouldn't see them if you graphed it on a calculator or a computer, but we use them to get us a more accurate picture. What are we missing? We're missing something big. The foci. So we use the formula c squared equals a squared plus b squared. So this is 16 plus 9. Exactly. C squared is equal to 25, which means that c is plus or minus 5. So we go over to positive 5. There's one focus. to go over to -5, and there's the other focus. So label one of them as focus 1, and another one is focus 2. It doesn't matter which one's which. And that's how you graph a hyperbola. You place the vertices, the b values, you draw the central box, you place the slanted asymptotes in there. Okay? Let's do another one. Then we better go. I think the bell's going to ring in a few minutes. For sake of time, let's just already have it in the form we need. Y squared over 4 minus x squared over 9 is equal to 1. What kind of hyperbola? Vertical. Because it's the y squared that's positive. Now, the next question is really important. Which one is a squared? Which one is b squared? This is a squared, even though it's smaller. Okay, this is a squared. A squared equals 4. B squared is equal to 9, which means that A is plus or minus 2. B is plus or minus 3.
Are all of ours going to work out this way? The ones that you're giving us?
On the examples, probably not the ones in your homework. So we got to draw the central box, and I've seen this mistake quite often. Where does A go on this graph? On the y-axis this time. Why does it go on the y-axis? Because it's a vertical hyperbola. Okay, so you got to place the A values on the y-axis. So go up to 2, down to -2. This is A and -A. Through those points, that's where the hyperbola is going to travel. Through those are the vertices. The B values go on the x-axis. Okay, you use those coordinates to draw the central box. I know I'm moving real quick here, but I think the bell's going to ring in about 2 minutes. What's the use of that central box? It gives us the shape or the slope of the asymptotes. So you go through the corner and through the origin of the central box. This is going to be a pretty wide hyperbola because it's got to follow the up and down asymptotes here, so it comes like that. And like that. And last, we need the foci. C squared is A squared plus B squared. So C squared is 4 plus 9. So C is equal to, well, actually it's plus or minus. So yeah, we just got to estimate. Square root of 13 is pretty close to square root of 16. So it's between 3 and 4, but closer to which one most likely? Probably closer to 4. So between 3 and 4, maybe closer to 4. So here's focus 1 and focus 2. Okay. Now, there is one more type of problem you have to be prepared for. Well, just, if the bell rings in the middle of this, so be it, but just kind of watch. Rather than graphing, they're going to give you some information. The foci would be 0 plus or minus 10. Vertices are 0 plus or minus 8. They would ask you then to give the equation. What would the equation of that hyperbola be, given that information? Well, let's first, what kind of a hyperbola is it?
Vertical or horizontal?
Vertical.
Well, there we go.
It is vertical because those are on the y-axis. We've done ones like this with an ellipse, so I'm sure you can figure it out.
Everybody.
So, because this is a vertical hyperbola, the equation is this. This is what you guys are going to be tested on. No, not you guys. It was my last class. Okay? Now, the vertices give us the value of a. If a is equal to 8, then a squared is 64. The foci give us the value of c. If c is equal to 10, then c squared is 100. So we know that the equation is y squared over 64 minus x squared. We don't know b squared. So we can find b squared using the formula c squared equals a squared plus b squared. C squared is 100. A squared is 64. You guys can actually figure this out. This is just Pythagorean theorem stuff. Help me out here.
100 minus 64.
Okay, that's 36.
And then square 36.
So b is equal to 6. B squared is 36. So now we know we can replace that with, well, we need to replace that with b squared, so it still stays 36. There's the equation of that hyperbola.